Hi, this is the final lecture for Math 310 at Simon Fraser University, spring of 2020. What I'm going to do is just, in the absence of any direct questions that I need to do for this review lecture, is I am going to go through the final exam I gave in the fall of 2017. And I'm going to just go through these questions. I'm going to solve them, make some comments as I'm going. You may wish to when you see the problem, you may wish to stop the video and use this as a practice, and then look at how I'm doing the solution, and because oftentimes there's more than one way to proceed, and or if you realize you can't make progress, then after watching you may realize what it is that you need to review or learn. So I'm going to proceed. I don't want this video to be too long. I'm not sure how long it will take me to go through, but if it gets to be longer than about 50 minutes, I'll stop, make this part 1, and then I'll do part 2 in the second video. If I can finish it all in the sort of 50 minutes to 1 hour time frame, then I'm going to do that. So this is an exam I gave in the fall of 2017 for the same course that you guys are now taking. Okay, so here's question 1. Is this a linear or nonlinear? So we have an initial value problem, first order, y prime equals y squared minus y, with one initial condition, y of 0 equals 2. Is it linear or nonlinear? So you circle the correct answer. So I'm going to do that. The correct answer is nonlinear. Why is it nonlinear? Because of this y squared. Okay, so that's not linear in the independent variable y. Okay, next question. Determine all of the equilibrium points. So an equilibrium point is when the function is not changing, and when a function is not changing, that means its derivative is 0. So we don't need to solve the differential equation to determine the equilibrium points. We just need to investigate when the derivative is 0. So I'll make a note of that. Equilibria. That is when the derivative is 0. And we see that in this question, the derivative is y squared minus y. So the derivative will be 0 when y times y minus 1 is equal to 0. And that implies that there are two possibilities for y, 0 and 1. So that those are the equilibria points. Now the question is whether those are stable, unstable, or semi-stable. So what I'm going to do then is just take a quick, I'm going to draw a line, and I'm going to indicate here, this is y, so this is 0 and 1. So I know that the derivative is 0 at those points. Now what I really want to know is what is the derivative on either side of the point. So I'm just going to do that via a test point. And so I'll look at some number bigger than 1. So I'm thinking, okay, y greater than 1. And then I look at the equation here, and I say when y is bigger than 1, both of those things are positive. So over here, the derivative is positive. So it is, the derivative is 0 here, and then some positive over here. And then I look between 0 and 1. So here's where in this one, I concluded that the derivative is positive. Then I look between 0 and 1. So I'm looking between 0 and 1, and I see when between 0 and 1, y is positive, but y minus 1 is negative. So that's telling me that the derivative is negative in this area here. So that's going to be somewhere down here. And then I look less than 0, y less than 0, and I see that both of those things are negative, so that means that y prime is greater than 0, so I have a positive derivative over here. So I see that what happens is for any y values here, the tendency is to increase. For y values in here, the tendency is to decrease because the derivative is negative, and then over here, the derivative is positive. Then looking at that, I can see that should I be here at 1, and I get perturbed a little bit a ways away from my equilibria point. For example, I come here, then the tendency is going to sweep me away. And if I come here, the tendency is to sweep me away. So 1 is a unstable equilibrium. So I'll make note of that. Y equals 1 is unstable. And then I'm looking at the other equilibria, and I see that when I am perturbed a little bit a ways away, the tendency is to going to be to force me back. And if I'm perturbed a little bit on this side here, the tendency is also going to be to push me back towards the equilibrium point. So I see that y equals 0 is stable. Okay. All right, so then I'm getting asked here to sketch the direction field, including the region where y is less than 0. Okay, so to do that, I'm going to just make a variety of points for the values of y, and then the values of y prime, which we know from the differential equation is y squared minus y. So I'm just going to pick some points, -2, -1, 0, 0.5, 1, 2, and 3. I'm picking some points. I make the calculation y squared minus y. So in this case, I'm just going to do one of these for you to see, but this is -2 squared minus 2, and that is 6. Okay, so I'm going to make that is y squared minus y when y is -2. So I'm going to make that calculation for each one of these things here, and I get these numbers here. I notice that y prime does not depend on t. That means that every column in the direction field is identical. We only have to draw one and then kind of copy it across as best I can. So I will draw the direction field. This is a plot where we have the independent variable here, t, and the dependent variable here, y. Okay, so now I know the values of the derivative. So let me just, here 0, let's just maybe make 1 here, 2, 3, like that, and then -1 and -2. Those are the values I've calculated. I see that when y is -2, the slope is 6, so that is very steep slope at -2. Let's draw that right here. And then when y is -1, it's still quite steep, a slope of 2, but is a little bit less steep. When y is 0, I see that there's a slope of 0. And then when y is 0.5, I got a slight negative slope. I'll put that here, slight negative slope. And then y is equal to 1, I have a slope of 0. And when y is 2, I have a positive slope like that, and then a more positive slope at 3. Okay, so I can draw that one column on the slope field, and then I can replicate that over because there's no dependence upon t. So I just try to do that as sort of neatly as I can, looking like this. So these columns should be identical to the one I've already drawn. So I replicate that a bunch of times, and I get a sense of what's happening. And looking like this. I can do it on the other side as well. All these columns are the same. Okay, and then we're supposed to sketch the trajectory for the stated initial condition. So what is the stated initial condition? That is here. Y of 0 is 2. That means at when t is 0, we are sitting here at 2. So we see that the trajectory will look like this here. It'll be going up here, and then we'll be coming somehow down like that. So we can sketch that trajectory on there. Okay, that's question 1. Next question. Okay, the parts of this question are unrelated. Okay, noting that, so I don't have to, well, if I can't do part A, I will still try to do part B, etc. like that. So take note of those little things at the top of the questions. Make sure that you, follow the instructions, and also notice things that make it easier for you to do the problems. Okay, so now the question here is, which of the following is an integrating factor for this differential equation here? So integrating factor, this is a first order linear differential equation, we can calculate the integrating factor mu of t in this manner here, the exponential function of the integral of p of s ds. Okay, which in this case is that's the general formula, and in this case it is this here. We are looking at this function right here. That is going to be minus 2s ds, and that is going to be equal to e to the minus t squared. So I box this one here. So finding an integrating factor. Okay, next question, finding which of these ODEs are exact. So like when it says this, which of the following, that of course means there could potentially be more than one, so all of them have to be checked. Okay, so let us recall the general form of the differential equation when we're thinking about it in this manner, thinking about checking for exactness. It looks like this, equals 0, and the differential equation is exact if the partial derivative of m with respect to y, I remember this as the word, I can see the word my, is equal to the partial derivative of n with respect to x. So I just need to go through and check that for each one of these differential equations. So I will do the first one. I'm looking at this one here. I can see that m is 2x plus 4y and n is 2x minus 2y. So I calculate dm by dy, and that is going to be 4, taking that's the partial derivative of that with respect to y. And then I take dn by dx, and that is this function right here. I take the partial derivative with respect to x and I get 2. 4 is not equal to 2, so this one is not exact. Go through the next one to the next question. Okay, I see it's written in a format that's I can't see directly, so I'm looking at question number 2. I can't see directly, so I just rewrite it in this form here, so I can make sure I have m and n identified correctly. And when I do that, I get minus 2y minus x plus 2x minus 3y y prime is equal to 0. And then I can see what m and n are, and I can compute the partial derivative. So I do it again, dm by dy, and I take, so I'm here taking the partial derivative of that. It's minus 2, and then dn by dx. I take the partial derivative with respect to x of this one, and I get 2. Nope. Keep going. Go on to question number 3. I would write this just dividing through here by dx, and similar, I'm going to just do this one at the same time like that. We're more used to seeing it like that anyways. So I go through like that, same thing, take dm by dy, where m is this function here. So I'm taking the derivative with respect to y. So I get e to the x cos y plus 3. And then I take the derivative with respect to n. The derivative with respect to x of n, which is that one right there. And that is going to be minus 3 plus e to the x sine y. I have failure to find another one that's exact. Okay, so let's go on to 4. I'm now on the fourth equation here. So I'm here. I have m and n. I'm taking the partial derivative dm by dy, and I get x over y plus x, and then I take dn by dx, and I get y over x plus y. So the fourth one, and I look at that, no, these are not equal either, so far I'm on a negative on that one as well. No, and then I'm hoping at this point that this one will come out to work, otherwise I I will have to go back and sort of check. I mean, of course, if you've made a small error, in fact, you can sort of see the possibility of danger here. If you made a slight sign mistake, you'll get the wrong conclusion. Okay, so 5, I'm going to calculate the derivative of m with respect to y. I'll write it this way. So this just to remind you, this notation my means dm by dy. Okay, so I calculate that as 1 over x, and then I calculate nx, and that is 1 over x, and voila, that one is an exact equation. So I'm just going to indicate that in red. So there we go. Okay, so that one is exact. Okay, next question. Find this general solution. It's first order separable. Okay. So I can write it this way. Oh, what happened? Sorry, let me just close that. It's first order separable. So I have x squared dy by dx is equal to y squared, and that means dy divided by y squared equals dx divided by x squared. And then I can integrate both sides, and I get the following integral here: minus 1 over y is equal to minus 1 over x plus c. And then I do a little bit of algebra on that, and I see that y is equal to x over 1 plus cx. And that is this thing right here. Okay, so let me just say that during the exam, should you be doing something and think, oh, there's something wrong with this question, I will be available via email during the exam time. So send me an email and then move on to another question, and I will get back to you as quickly as possible, either telling you, no, there's nothing wrong, proceed to do the best you can, or telling you, oh, shoot, there is something I overlooked there, or there's a typo or something like that, and I'll get it fixed. So feel free to contact me like you would do, in person if we were having a final exam. I will be available the whole time. Okay, next question number 3. Again, we notice the parts of the question are unrelated, and we want to circle the letters corresponding to the correct answer. So here's a statement. Let y1 and y2 be a fundamental set of solutions to a differential equation, which we notice is linear, homogeneous, and it's on some interval a, b. Now consider the 3 statements. The Wronskian of y1 and y2 is non-zero everywhere on a, b. That's a statement. Y1 and Y2 are linearly independent. That's another statement. And Y equals C1 Y1 plus C2 Y2 is a general solution for C1, C2 arbitrary constants. And it's asking you which statements are true, if any. And then there's a whole combination. So rather than try to, in fact, look at these and sort of second guess it, which most of the combinations are there, I'm going to try to look at which ones are most obviously true or false, and then think about the other ones from maybe more carefully. So when I look at these 3 statements, it's a fundamental set. For sure, they have to be linearly independent. So I'm immediately coming here and thinking, okay, this is true. So 2 is true. So that eliminates that. That eliminates that. And that's all. So I've reduced the possibilities now down to 3. When I have 2 linearly independent solutions, then the general solution is a linear combination of those 2. That's for sure true. I think that's the next most obvious statement. So that one is also true. So 3 is true. So I have right now 2 and 3 are true. So that eliminates this. So I'm down to two choices, and that's going to be based upon whether 1 is true or 1 is false. Okay, the Wronskian is non-zero everywhere. No, that is false. Okay, that is maybe a little bit trickier to see. The Wronskian is either going to be 0 everywhere on the interval, or it's going to be some number everywhere on the interval. So that statement is false. So that means the correct answer here is 3. Okay, a question about linear independence of two functions, or in fact, for what value. Okay, so there's actually a, oh, sorry, I read the question a bit too quickly myself. I'm looking again for what value of the constant a. So I see there's a constant here, and it's asking me for what values of a are these two functions linearly dependent. Okay. So I make sure that I understand then what's the definition of linear independence or linear dependence. And so I'm thinking, okay, hang on, I'm going to take a linear combination of these two functions, 2t squared plus 3 plus c2 times at squared. And I'm going to see for what values of C1 and C2 would this statement be true? I mean, it's not a possibility for me to have C1 and C2 equal to 0. Okay, why not? Okay, so C1 equals to C2. Not possible. Because if that's the only possibility, then they would be linearly independent. So I have to be able to find values of C1 and C2 that are both not 0. Okay, so this is the sort of, I get this statement right here. Understanding this statement right here is to make sure this statement is possible for you to make quickly if you are clear about the meaning of linear independence. Okay, so now I'm looking at this. I've got I'm adding on the left-hand side two polynomials, and on the right-hand side I have 0. So I can form two equations and two unknowns from this. And I can see on this side here, the constant term is 0. And over here, the constant term is C1 times 3. There's no constant term here. So this tells me that 3C1 is going to have to be equal to 0. That tells me that C1 is 0. Okay, next thing is that that will mean that in order for this statement to be true, without making C2 0, I need to have that C2at squared is equal to 0, and I do not want this to be made true by having C2 equal to 0. That tells me that a must be 0, because that's the only other way to make this equal to 0. So that is option number 3. Okay, next question. What's the largest interval that the existence uniqueness theorem guarantees a unique solution to the initial value problem? So I'm looking at this. I'm knowing that I'm going to have to be thinking of a theorem, and the theorem is different in the linear and nonlinear case. So first thing I'm thinking is, okay, let me be careful. Check if it's linear or nonlinear. I see this one is linear. Okay, so we're in the linear case. I notice initial condition, and that's a second order system. So I've got two initial conditions, and I notice that the initial condition is at t equals 2 is the point where we have the initial condition. That's likely to be important because if we find any discontinuities, we're going to have to be where the value of t is in the correct interval that is demarcated by the discontinuities. Okay, so then I write the differential equation in the standard form. That looks like this. Okay, and I see then I can identify P of t. P of t is 1 over t squared sine t, and Q of t is minus 2 over t cubed times t minus 5. Okay, and it's pretty easy to see now where the problems are, the discontinuities. So I'm looking for the discontinuities in P of t and Q of t. And where are those? Those are at t equals 0 because of this, well, that problem, and also the sine function is also 0 there, and also that's the t equals 0, and then I'm seeing t equals 5 is also a problem. And then, oh, I have to be a little bit more careful about the sine function. It's because the sine function is not just 0 at 0, but it's also 0 at any value of n pi n in z. So it's important to identify all of the discontinuities. So maybe if I just now drew a number line, and I'm thinking here of t, and I've got 0 and I've got 5, I've got the discontinuities there. I've also got them at n pi. So there's going to be pi is going to be here, and then I'll have a minus pi here, and then somewhere over here I'll have 2 pi, like that. So this is where the discontinuities are, and there's more of them. There's continuing up and down, but I'm not worried about that because I know that I'm near 2. So then what I do is I look and I'm imagining the discontinuities to be sort of walls, if you will, like this, like that. And then I'm thinking, okay, well, when I'm at 2, where I know I have an initial condition, that is, this number is 2, then I'll be able to maneuver in here, but I am not going to be able to move up like this. That's not going to be happening because there's a discontinuity at pi. So then I identify that the theorem is going to guarantee me a unique solution in the interval 0 pi, and that is option 3 here. Okay, question 3. Moving on to question 4, which I have to admit I'm looking at a fair bit of algebra happening here. I will do as much of it as I can. Okay, so here we have an initial value problem. You can see that it's the homogeneous part of it. This part here is constant coefficient. Okay, so that right away you might want to think, okay, so it's a constant coefficient. Corresponding homogeneous differential equation. That is easy to solve. And then I'm looking at what the forcing function is here, and I see that it is fairly simple and it's a sine function. So definitely I could use the method of undetermined coefficients. That is what I will do. You could also use the method of variation of parameters. Okay, so there's a couple of options. Choose which one you think may be less painful. I'm going to do the method of undetermined coefficients. If you wanted, for that matter, I mean, you could do a solution here using the Laplace transform as well. Okay, so I'm going to do the method of undetermined coefficients. Okay, so step 1 will be to solve the homogeneous equation. Okay, that's homogeneous equation is y double prime plus 9y is equal to 0. We do that with the characteristic equation, and that is going to be r squared plus 9 is equal to 0. We find the two roots of that. That is going to be r equals plus or minus 3i. And then that means our solution to our homogeneous equation is c1 cosine 3t plus c2 sine 3t. Okay, right at this point then the alarm bells should go off, because you see that the forcing function here, sine 3t, is already represented as part of the complementary solution. So we have to be careful when we choose the form of the particular solution. Okay, so I am going to postulate. Okay, so what I do is I postulate the form of the particular solution with that in mind. Okay, and this is our to t or not to t thing. So because I see I cannot just postulate sine 3t plus cos 3t, which I would would be my gut instinct on this at the top, because that came out to be solution of the homogeneous equation. So I have to multiply by t, and I get that I get a particular solution. A postulate of the particular solution is going to be at cos 3t plus bt sine 3t. Okay, it's important when you have the trigonometric function sine or cosine as a particular solution, as the forcing function, that you incorporate both the sine and the cosine. It's not just the sine here, it's both the sine and the cosine postulated. Okay, then I have to go through and take the first and second derivatives, substitute into the differential equation, and figure out what is A and B. That is my goal here. Okay, it's a bit painful, but let's go ahead and do that. So I will take the derivative. That is going to be A cosine, using the product rule, minus 3AT sine 3t plus B sine 3t plus 3b t cosine 3t. Take the second derivative. That will be minus, let's see here, I'm looking at this. I've got A cos 3t. Let me just put what I've got here, then I'll check. I've got 3A sine 3t minus 3A sine 3t. That's coming from that one. And no, sorry. Let me slow down slightly here. Okay, I'm taking the derivative of this. I'm taking the derivative of the first term first. Okay, taking the derivative of this, I get this. Now I'm going to take the derivative of this, and I'm going to get this, minus 3A sine 3t, using the product rule here, minus 9AT cosine 3t. And then I'm going to take the derivative of this one here, plus 3b cosine 3t, plus, and then I do this one last, 3b cosine 3t minus 9bt sine 3t. Okay, if it were me on an exam at this point, I would maybe stop here on this problem and go on do the next problems, particularly if I thought that my understanding of the material was strong and I would not be slowed down and possibly making a mistake in doing a bunch of algebra here and consuming a lot of time. And then I would come back to this question closer to the end. Okay, so I'm going to now substitute in this, and this. Well, mercifully, I actually don't need this. So I'm going to substitute in these two things into this here, yp double prime plus 9yp is equal to minus 6 sine 3t. So that's the differential equation. I'm now going to substitute my proposed solution for the particular solution into there, and I'm going to try to figure out what is A and what is B. So I go ahead and do that. I get this here, minus 3A sine 3t minus 3A sine 3t minus 9AT cosine 3t plus 3b cosine 3t plus 3b cosine 3t minus 9bt sine 3t plus 9AT cosine 3t plus 9bt sine 3t, and that whole mess has got to be equal to minus 6 sine 3t. Okay, it's not quite as bad as it looks. This is canceling out, with this, and this is canceling out with this, so I get some cancellation happening, and some things also combine. Some terms combine. Those terms are these ones here, minus 6 sine 3t plus 6b cos 3t. Okay, and that's got to be equal to minus 6 sine 3t. Okay, there's no cosine on the right hand side. That tells me right away that b has to be equal to 0, and then I see that because of this minus 6a and the minus 6 here, I see that a has to be equal to 1. So now I know what is a and b. Then I now can easily write the particular solution. It's actually quite simple. It looks like this. A is 1 and b is 0, so it simply looks like this: t cosine 3t. That allows me then, now that I've got the solution to the homogeneous part of the equation, and then I've got a particular solution, I can combine those two for the general solution. So y of t equals the homogeneous solution plus the particular solution, and that is going to be c1 cosine 3t plus c2 sine 3t plus t cosine 3t. There it is. And the final step is to use the initial conditions to determine C1 and C2. Okay, so I simply substitute in for t equals to 0, and I get y of 0, and I calculate out what that is, and y of 0 is equal to C1 cosine 0 plus C2 sine 0, which is 0, that's gone, plus 0 times cosine 0. So that means I immediately can figure out that, and what is y of 0 equal to? Y of 0 is 0. So that's the stated initial condition, y of 0 equals 0. So that tells me that C1 is equal to 0. And then I have to take the derivative. That's my second condition. I need y. I know what y prime at 0 is, so I need to know what y prime of t is. So I'm going to just take the derivative of the function y of t, and I'm going to get 3 c2 cosine 3t plus cosine 3t minus 3t sine 3t. And then I evaluate that at 0, and I know that that is supposed to be equal to 1 because that's my initial condition, and I get 3c2 cosine of 0 plus cosine of 0 minus 0. That tells me that 3c2 plus 1 is equal to 1, and that tells me that c2 is also equal to 0. That allows for a very simple equation here. It's t times cosine of 3t. Okay, there we go. Okay, so it's a fairly long procedure, the method of undetermined coefficients, but it's relatively straightforward. Critically, you must postulate the correct form for the particular solution. Okay, the next question, Laplace transforms or inverse Laplace transforms. So what is we're supposed to do here? The Laplace transform of y of t equals what? So here's the question, y of s. Okay, and so we don't not being asked to in fact find y of t. So be careful, don't do extra work, right? It's not asking to solve this differential equation. It's merely asking us to find y of s, the Laplace transform of the solution of the differential equation. That's much easier. Okay, so I go ahead taking the Laplace transform on both sides of this equation, and I get s squared y of s. So certainly you must know what the Laplace transform of the second derivative and the Laplace transform of the first derivative of a function is. For sure that will come up on the final exam. Okay, and then I'm here for s y of s. So this piece right here, that is the Laplace transform of y double prime. Now I'm doing 4 times the Laplace transform of y prime, and then I'm doing the Laplace transform here, which is that thing there. And then I take the Laplace transform on the right hand side. What is the Laplace transform of t e to the t? And that is 1 over s minus 1 squared. That's my dog getting excited about Laplace transforms. Okay, so let us just, perhaps this last step here not as clear, totally clear. So let's just, I'm thinking here about taking the Laplace transform of that function on the right hand side, and that is equal to g of s minus 1, where g of t is the Laplace transform of t, and that is 1 over s squared. Okay, that's how that's coming up. So then that's, well, that's equal to the 1 over s minus 1 all squared. So now I can use the initial conditions here to fix these constants here. So I'm seeing got these initial conditions that is going, those things are going to go in here, here, and here. And that's going to allow some things to simplify. So one of them is 1 and the other one is 0. So that's going to simplify quite nicely. And I'm going to get s squared y of s minus s plus 4s y of s minus 5 y of s is equal to 1 over s minus 1 squared. Okay, then all I have to do now is factor out the y of s and write y of s on the left-hand side and everything else on the right-hand side. So I'm going to do that. I'm going to factor out the y of s out of the terms. So y of s is sitting there, there, and there. So it's going to be s squared plus 4s plus 5 times y of s. Okay, first thing to notice is this thing right here. You can see that right here. You can just sort of be imagining that thing as a homogeneous differential equation. This is looking exactly like the characteristic equation. Okay, that's not a coincidence. And then what else is left? When I do that, I have those things. What other term is there? There's an s here, and there's a, whoops, I think I've lost a term actually. Yep, I've lost this term right here. Okay, so there's there should be plus 4s. Sorry, when I was doing this here, there's a minus 4 and a minus here. So there's a minus s plus 4 here, and then that is equal to 1 over s minus 1 squared. And then I'm going to put the y of s. This is what I'm asked for. I'm asked for y of s. So I'm going to put my answer as y of s, and it will look like this. 1 over s squared plus 4s plus 5 multiplied by s minus 1 squared. That's the, and then I'm going to have the second term, which is going to look like this. S plus 4 divided by s squared plus 4s plus 5. Okay, there we go. Oh, okay, I'm going to make a correction here on the on this exam here, and this was actually changed during the exam when I realized I made this unfortunately more difficult than it needed to be by having the m there. So I just replaced that by pi, and that's so we can just have one complete cycle of the sine function. So we've got we've got sine t I'm thinking here for a second. Let me just draw it. So the function looks like this. There's the sine function, and that value there is pi, and then so it's 0 otherwise. So I am thinking of applying. So the sine function would be obviously continuing here. So what I need to do is then take a look at what have a step function happening here. Let's think here for a sec. It's sine up to there, and then I have something is going to change here, and this is pi, and this function here is u pi of t. Okay, so what I want actually, in fact, is the inverse of this. I first want to have this available, and then at this time I want to step something up. So first I'm going to step the sine function in, and then I'm going to step it back out. Okay, so that means f of t is going to look like this. F of t is going to be sine t multiplied by u0 of t. So at time 0, the sine function kicks in, and then at time pi, the sine function has to be removed because it goes back down to 0. So this is u pi of t. Okay, then I can now start to think about how to take the Laplace transform, and so the Laplace transform of sine of t is 1 over 1 plus s squared. That's with s greater than 0. Okay, so now I need to understand, well, what I'm doing is looking on the table of Laplace transforms, which you will be allowed to use on the final exam. And I know this fact here, f of t minus pi. I know this from the table. That is e to the minus pi s f of s. Okay, so that's from the table. Both of those two things are from the table. So now I'm thinking, okay, I need to deal with this situation here. And this is the tricky part in this question, actually. And I made a video of a question that a student asked me. It's a video I posted just before this one for Math310. And that is about, we see this here, therefore that has got to show up inside here, or we cannot use this. Okay, so there's another example of this, of how to manipulate this, in a previous video as well. But that is the tricky part. So I'm focusing on this here, and then I am going to use this the sine of t minus pi. Why do I want to make it t minus pi? Because of this pi here. So I want that is minus sine t. So I can change this sine t to minus sine of t minus pi. So I'll rewrite my function this way. F of t will be sine t. We're at t greater than 0. So, and then there's going to be a plus sign here, and this is going to be u pi of t times sine of t minus pi. Okay, the tricky step going from this circled portion to this portion right here. Now this is extremely straightforward. Then you can well, it's not going to be equal. We're now going to take the Laplace transform of that. The Laplace transform of that function is going to be the Laplace transform of the sine function. That is 1 over 1 plus s squared, plus the shifted version of the sine function. Okay, there we go. Okay, Laplace transform using the unit step function. That thing is very, very useful for forming functions and then being able to take the Laplace transform. Okay, next question. Okay, what am I asked for? Oh, I'm being given a function of s with capital F. So immediately I'm thinking this is a Laplace transform. And then I see, oh, I see. I'm being asked to take the inverse Laplace transform of this. So I look at this, and I'm going to do a inverse Laplace transform, and then the first thing I'm thinking is, okay, it is a rational function, so there's going to be two possibilities of things I would consider: partial fractions or completing the square. So the first thing I want to understand is this, can I factor that or can I not factor that? Because that's going to make a difference on which way I go. So I'm looking to see whether I can factor that quadratic into linear factors or not. So I check the discriminant. So that's my first step here. I'm looking at this function right here, s squared plus 4s plus 13. I'm going to check the discriminant, b squared minus 4ac, and that is going to be 4 squared minus 4 times 1 times 13. And as soon as I write it like that, I can see that's less than 0. So that means that this function here is an irreducible quadratic. So then I will not be doing partial fractions because because I can't factor it. I can't factor it over the real. So I'm thinking, okay, I want to complete the square. So I will do that, completing the square on here. 4s plus 13, and that is s plus 2 squared plus 9. Okay, completing the square. Okay, I am now looking at the form of this, and my attention has shifted here to this numerator, and I'm going to write that numerator like this: 2s plus 16. I'm going to write it like this: 2s plus 4 plus 12, which is equal to 2 times s plus 2 plus 12. I did that because I saw this s plus 2 here. Okay, now I have an s plus 2 here. So now I'm going to rewrite the Laplace transform down here with my modified numerator and my modified denominator. So I completed the square in the denominator. I use that information to see how I should nicely write the numerator. And now I'm going to divide the denominator into the two pieces of the numerator. So now I'm thinking of the numerator in two pieces, this piece right here and this piece right here. And I am going to divide the denominator into those two pieces. Okay, so that is going to be 2s plus 2 over s plus 2 squared plus 9, and 12 divided by s plus 2 all squared plus 9. All right, so now I can take the Laplace transform of these two pieces independently, and they are now very much like something that I can get from the table. So let's try getting the Laplace transform of the first of those two pieces. The inverse Laplace transform of the first of these two pieces. That inverse is 2e to the minus 2t times cosine 3t. Okay, and then the inverse Laplace transform of 12, I'm going to write that as 4 times 3 over s plus 2 squared plus 9. And the inverse Laplace transform of that is 4e to the minus 2t sine 3t. Okay, I would be somewhat surprised. It's maybe not impossible, but I would be somewhat surprised if those two things didn't come out to be like sine and cosine of the same argument, because we often see in solutions to differential equations that they come in pairs. So just those sort of things. If it didn't, I would be thinking, maybe I should look back and check. Okay, so now I can write what f of t is. I'm going to just factor out that e to the 2t, and I'm going to get here 2 cosine 3t plus 4 sine 3t. Okay, it's been 54 minutes, and I just finished question 5, and it is the case, in fact, that there are, I'm just making sure, 10 questions on this test. So I think that's a good place for me to stop. This will be part A, and I will be back with part B, starting with question 6 and solving the remaining portion of the exam. Thank you.